as I. So every time you see the square root of -1, you're going to replace it with an I. And then we're going to use this property to simplify negative radicals. So let's use this property that's on your papers. The square root of -49, we would write as -1. We pull out that -1 since we know how to define that. And then we use our exponent property since the square root is an exponent. It's the exponent 1/2. So we take the square root of each one of our factors, and we get I times 7. So you can either write it as I times 7 or 7 times I. So that's how we would simplify that. The square root of -8 is very similar to what you did in your preview exercise, except for now it has the square root of -1. So all of you simplified the square root of 8 as 2 square roots of 2, and now you have an I in front of it. So typically, typically that's what I was just about to say. Typically when we have a multiplication problem, we know the order doesn't matter. So the standard way to usually write this, even though it doesn't matter, is to put your rational number or your real number in front. Not your real number, because your rational number in front, followed by I, followed by your irrational number. But again, it doesn't matter which order you write it. You could write square root of 2 times I if you want. It doesn't matter. Okay. Typically, we don't put the I right after the radical because sometimes it's not clear where it exists. You know, is it under the radical or is it outside? This is the power of I that you're going to use the most in terms of the rest of this course. So we want to be able to define what I square is. So if I is the square root of -1, what do you think squaring -1 will give you? -1, right? Because when you square a square root, they undo each other, they're inverse operations. So I square is -1. So that's the other thing you sort of have to put in your memory banks. I square equals -1. You're going to be using it quite a bit. The other little thing I wanted to point out is that when we were working with real numbers, we were working with this equation that goes both ways. However, when we're dealing with negative radicals, we don't want to squish those back together. We don't want to call that the square root of -20 times -5, which is 100, because we'll get the wrong answer. So this property is not going to be used when we evaluate expressions that have negative radicands. All right, so what we want to do is evaluate each one individually. So this one will be square root of -1 times the square root of 20 times the square root of -1 times the square root of 5. Well, square root of 5 is already irrational, so I'm going to make that blue. There's nothing we can do with that. Can we simplify anything else here? Replace it with anything else, any of the green factors. Okay, so we get 2i. Where did the I come from? Right, square root of -1 can be simplified to I, and then square root of 20 can be simplified to square root of 4, square root of 5, which is 2 square roots of 5. And then we've got one more I coming out of here. There we go, square root of -1 is another I, and we've got the square root of 5. So notice this is all multiplication all the way across. So I'm just going to regroup it. I'm going to put I's beside each other. My 2 is kind of all by itself, and then I have 2 square roots of 5. So that gives me I squared times 2 times the square root of 5 squared. And now I know from the work we did above that I square is -1. So that's -1 times 2. And that the square root of 5 squared just gives me a 5. So my answer is -10. Okay. So now you can see why I can't call this the square root of 100, because you wouldn't get -10, you'd get 10. So when you're working with negative radicals, you want to simplify each radical and then continue to evaluate. Any questions on that? Okay. All right, so quadratic equations. Any quadratic equation, the highest power you'll see on your variable is going to be a 2. And that's why we call it a second degree equation. As you know, first degree equations are called linear equations. In general, the general form of a quadratic equation is written like this. Notice it's always set equal to 0. We have all of our terms on one side, and the only condition here is a cannot equal 0. Why do you think we say a can't be 0? Why do you think we have to put that little condition in? Why can't we just leave it as ax squared plus bx plus c? That's right. If a was 0, 0 times x squared is 0, then you'd be back looking at a linear equation. But a, b, and c belong to the real number set. So they can be any real number. They could be square root of ugly numbers. They can be ugly fractions. They can be nice numbers like 2 and -10. Okay? So let's take a look at some of the strategies. There's 3 strategies really for solving quadratic equations. One strategy works for all quadratic equations, and that is the quadratic formula. You can always use a quadratic formula no matter what your original equation looks like. So what I want to try to do for you is I just want you to see what some of these quadratic equations look like if we categorize them. Let's take a look at a situation where b is equal to 0. So that means we don't have our middle term. This middle term we call the linear term because the power on that x is 1. So it's called the linear term. The ax squared term is called the quadratic term because that's the one with the power of 2. And the c term is called your constant term because it's just a constant. So sometimes we have quadratic equations with all 3 terms. Sometimes we just have it with the quadratic term and the constant term, which is what we're going to look at in this first situation. So the very first type of quadratic equation we're going to look at is something like this, where we have our quadratic term equal to a constant or a bunch of stuff squared equal to a constant. And so this type of quadratic equation can lead students astray. And we talked about this earlier, maybe a week or so ago, when we looked at something like this. But instead of having a -25 over there, we looked at a positive number. So let's just put this aside for now. I'm going to block it up here. Let's just put something over. Oh, I guess that won't block it. All right. Instead of trying to get fancy here, I'll just forget it. So we're going to have too long of a lecture today if I try to get cute here. So let's go back to this idea. Remember, we talked about solving this equation together as a class. And I warned you, remember that this can get you into trouble because we often leave out a step. And I often see this. This is what I see. I see this kind of thing, and I see this kind of thing. And that's going to lose half credit. Because when you see an equation like x squared equals 25, there's 2 answers. If we graphed x squared equals 25 and if we do this, then it's going to look something like this. If I graph that, where this is 0, -25. Nope, excuse, 0. What am I doing? Yeah, that's the y-axis. I mean the y-intercept, right? 0, -25. When x is 0, y is -25. And notice it goes through your x-axis, your x-intercept. There's 2 of them. So when you set a quadratic equation equal to 0, this is what you're finding. Now notice a parabola can go through the x-axis twice, once, or nonce. I made that up, nonce. Because your quadratic equation could sit totally above or below, like this. That has no x-intercepts that are real numbers. That's where we get into our imaginary numbers. So what you need to keep in mind is that you should be looking for 2 answers. So that when you come up with something like this, you know you forgot something. And if you recall, I talked to you about this as that the square root of x squared is this. And that has 2 answers for x. +5 can go in between the absolute value and -5. Okay, so if you have a tendency not to remember these kinds of things, that's okay, because anytime you see an equation like this, set it equal to 0 and factor it. That way you'll always get your two answers and you'll never have to worry about remembering the plus and minus. So let's take a look at x squared equals 25, and then we'll see what we do with x squared equals negative 25. So if you had x squared equals 25, that falls under this scenario where your middle term has disappeared, b is 0. When you set your equation equal to 0, you get the beautiful type of factoring you always want to see, the difference between squares. Because when you have something set up like this, the factoring is very easy. You know you lose your middle term because you have a plus and a minus, and everything is identical. You just take the square root, you say x times x is x squared, and 5 times 5 is 25, you're golden. And then you get your two answers for free, 5 and negative 5. Okay? Guess what? When we have a negative over here, before you were taught you can't factor sums of perfect squares, which you can't with real numbers. If I had x squared plus 25 there, you'd say it was prime. Now we can, because we have the square root of negative 1. So yay! So we add 25 to both sides. And now all you have to remember is it looks almost identical to what you had when it was the difference, except for now instead of just a 5 here, it's 5i and minus 5i. So your two answers here when you set this equal to 0. So x plus 5i equals 0. So x must be negative 5i. And when you set your other factor equal to 0, it's got to be positive 5i. So you say, wait a minute, Linda, I'm not sure I believe you that I can factor that. So how do you check it? You use your distributive property twice, which some of you know is FOIL, but it's just using your distributive property. X times x, x squared. Your middle term is 5ix. Your outer term is negative 5ix. They're opposites. There's your b0. B is equal to 0. And then you got this thing, 5i times negative 5i. 5 times negative 5, and I times I. 5 times negative 5 is 25, negative 25. I squared was what? Negative 1, and there's your 25. Okay? So it's really cool once you really believe that this factorization is almost identical to the difference between perfect squares. You don't have to suffer. You just do it as if it were 25, and then you put the little I after it. Okay? So we now can factor sums of perfect squares, no problem. So if you have this type of situation, you could factor it. You don't have to rely on that square root method and remembering plus and minus. However, if you do, this is what I want to see. I either want to see this on your paper and leave out the in-between stuff. If you remember the plus and minus, that's fine, but I don't want to see this. Because the square root of x squared is not equal to x. If you put that in, then I'm fine. So either leave out this step altogether or just go right down to your plus and minus. So I don't see what you're really thinking, all right? Because that's the one time I don't want to see you thinking. Okay, so this idea of using, making it a multiplication problem that's equal to 0 is this property right here. And this property, the zero product property, helps us to solve quadratic equations with factoring. So let's do this really quickly. I'm going to take this quadratic equation. I'm going to add 24 to both sides. And now I'm going to factor this equation. Factors of 24 that add up to 11 are 8 and 3. They're both positive. The order doesn't matter. And now I use this property because now I have two things that I multiply to equal 0. So I say, hey, when is this thing equal to 0? When x is negative 3. And when does this factor equal 0? When x is negative 8. Picky math teacher coming in. Notice everything that I'm solving here is an equation. Do not leave off this 0 because this is not equal to this. This is an expression. This is an equation. Every time we solve an equation, we rewrite the equation as an equivalent equation. So that's factoring. Factoring, when the equation doesn't have a lot of big numbers in it and it's easily factorable, I really encourage you to use this method. It's very simple. Okay. Of course, if I was looking at something like with 24x squared and a huge number here and another big number here, I probably wouldn't factor it. Okay. So let's take a look. Oh, so how would you write this in your My Math Lab? Remember, they're always looking for the solution set. You'll have two solutions. So what order do you think you write it in? Huh? Descending. Ascending. The smaller number, right? So you'll put -8, -3, right? Okay. I just wanted to point that out. Okay. All right, let's do this quadratic formula. How come we learned our alphabet when we were little? Well, so we could read, but why do you think little kids can go A, B, C, D, E? Why do you think they can do that? What is it that little kids, it's in song form. We tend to remember stuff, right? When it's a song and you sing it over and over. So watch this little kid. She's got a, you can see she wants attention here from her little sibling, girl, sister. Is that cute or what? That's totally cute. Look at her. She's so excited. All right. What song did she put that to? What melody? Right. So we're going to practice right now. Okay, I'll do it first, and then you're going to join me. X equals -b plus or minus the square root of b squared minus 4ac. And I can't reach it anymore. All over 2a. All right, ready together. X equals -b plus or minus the square root of b squared minus 4ac all over 2a. One more time. Come on, Alex. I want to hear you. X equals -b plus or minus the square root of b squared minus 4ac all over 2a. Okay. Why? Right. All right, so let's solve this equation with the quadratic formula, and then you're free to start exploring your class activities. Again, if I had this formula on a quiz or a test, what do you think I would do? Huh? Sing? Did she say sing? Huh? Cry? No. Solve it. I would solve it, but I wouldn't use a quadratic formula because you can factor this very easily. Factors of 7 that differ by 6, 7 and 1. I can do that really quickly, not a lot of mess. So anytime you can factor a quadratic equation, you're going to get a really nice number under the radical. Okay? So let's do this. First, we have to identify what A, B, and C are here. A is, B is 6, and C is -7. So since C is negative, I put a little star there, and I remind myself that my subtraction symbol inside is going to change to addition before I'm done. So I'm also going to add these little parentheses to the 4ac just so that if it is a negative number, I don't mess up. So the opposite of -6 is 6 plus or minus. -6 squared is 36 minus 4. I put my brackets. A is 1 and C is -7. All over 2 times A, which is 1. X equals 6 plus or minus 36 plus 28, because you're subtracting a -28. All over 2. 6 plus or minus the square root is 64, and you say, it's a nice rational answer. x equals 6 plus 8 over 2, which is 7, and x equals 6 minus 8 over 2, which is -1. So in your math lab, my math lab, you put -1 comma 7 as your solution set. Have a fun time with the activities. They're going to take you the rest of the class. Okay.